Welcome to This Explainer. I'm going to be your technical mentor today, and we're going to prepare you to absolutely crush one of the most notoriously tricky engineering prompts out there, the complex high-rise elevator system design interview. We're breaking down exactly how to architect a system that seamlessly handles rigid physical constraints, real-time control, and heavy distributed software. Now, this concept right here perfectly illustrates why interviewers absolutely love this problem. It strips away all those memorized textbook software patterns. I mean, you can't just throw a standard web framework at an elevator system and call it a day, right? It forces you, the candidate, to bridge physical constraints, like how fast a giant metal box can literally move, with extreme software scalability. You have to safely coordinate multiple moving cabins, deal with highly skewed traffic demands, and somehow hit these precise sub-50 millisecond latency limits. So here's our roadmap. We're going from ground zero all the way to the penthouse. We'll cover API design and telemetry, low-level concurrency, algorithms and destination dispatching, scaling to skyscraper demands, hardware failures and edge cases, and finally, KPIs and shadow tuning. Let's just dive right in.
All right, kicking things off with Phase 1, API design and telemetry. The very first step to a clean architecture is defining our boundaries and cleanly separating how data flows into and out of our central system.
A brilliant way to impress your interviewer right out of the gate is to separate your communication protocols based entirely on data direction. For the upstream path, so when a user actually presses a hallway button, we use stateless HTTP post REST calls. Think of this like sending a quick text message. It's completely fire and forget, which makes these client requests incredibly easy to balance and rate limit. But for the downstream path, like updating those little floor displays with the elevator's current position, we use server-sent events, or SSE. This streams the telemetry continuously over a persistent connection. It's kind of like tuning into a live radio broadcast. Even if the network is shaky, SSE has this built-in auto reconnection, so those floor displays stay updated in real time without totally overwhelming your servers. Moving down a level to Phase 2, low-level concurrency. How do we actually prevent software bugs from crashing a physical moving car? Well, when dealing with hardware, traditional software threads can get super messy. So the crucial point here is using the state pattern. Instead of writing messy, honestly dangerous if statements for every single physical transition, things like if direction is up and speed is greater than 0, then do this. We isolate the logic into dedicated classes. Think of it as swapping out entirely different instruction manuals. When the car is moving, it exclusively reads from the moving state manual. When it stops, it physically swaps that out for the idle state manual. This cleanly modularizes the behavior and ensures we don't accidentally say open the doors while zooming past floor 5. Furthermore, to manage the complex concurrency of multiple requests, you can easily sidestep those nasty database lock issues and race conditions by implementing the actor model. Essentially, this gives each individual elevator car its own private, highly secure mailbox. The car acts as a single writer loop, pulling and processing exactly one instruction from its mailbox at a time. This guarantees thread safety without needing heavy, slow database locks slowing everything down. Okay, on to Phase 3, algorithms and destination dispatching. Now let's tackle the real brains of the operation, how the system actually routes these cars efficiently. You really want to contrast the classic look algorithm against modern destination dispatching. The look algorithm is your baseline. It just sweeps continuously up and down the shaft, fulfilling requests along the way. It's very much like a public bus on a fixed route. And hey, this is great for saving mechanical wear on the cables and motors. But modern super towers use destination dispatching. This is where you punch in your floor at a kiosk before you even get in the car, allowing the system to group passengers going to the exact same floors together, which vastly reduces the total number of stops. Now, here is the ultimate multi-car coordination question you need to be ready for. When I press the up button on floor 4, how does the system actually calculate which of the 3 moving cars should be the one to pick me up? This brings us perfectly to the figure of suitability formula. The central dispatcher runs this mathematical check against every single active car in the shaft. Under Rule 1 of this formula, a car that is already traveling toward the request in the same direction instantly earns a much higher suitability score just based on its proximity. Conversely, Rule 2 heavily penalizes cars that are moving the wrong way. But we don't just rely on static math here. We apply dynamic coefficients to tweak the entire formula based on current skyscraper traffic patterns. We even factor in a coincident call bonus. Basically, if a car is already stopping at floor 4 to let someone off anyway, we give it a massive bonus to pick up our new passenger there too. It's essentially getting two birds with one stone.
And when you're discussing how destination dispatching optimizes transit, you absolutely must mention the pain index. This is a truly fascinating cost model that acknowledges human psychology. Passengers absolutely hate waiting in the lobby, far more than they hate moving inside the cabin. So the math violently penalizes wait times once they cross that 30-second mark. This curve steepens dramatically to prevent passenger starvation, ensuring absolutely no one is left stranded on a quiet floor for 10 minutes straight.
Next up, Phase 4, scaling to skyscraper demands. So how on earth do we take all this dispatching logic and distribute it safely across a massive high-rise tower without creating massive system bottlenecks?
To really wow them with your scaling knowledge, you need to lay out a 3-tiered storage architecture. You must clearly separate the rapid, sub-second telemetry from your historical event logs and persistent configuration data. We do this using Redis, Apache Kafka, and PostgreSQL, all working in harmony.
First off, we rely on Redis acting like a lightning-fast, short-term memory notepad. It holds the real-time telemetry, the exact speed, the direction, and target queues of every single car. Because it stores all this data in memory, the dispatchers can access and update these states instantly, without any lag.
Meanwhile, Apache Kafka functions as our indestructible flight recorder. It acts as a rock-solid, append-only event log. Every single button press, every sensor trigger, every door open event, it is all published right here. This guarantees that absolutely no data is lost if the system goes down, and it completely decouples our rapid telemetry from our downstream analytics and reporting. Let's look at the safety net and see how this builds our fault tolerance. We run the central dispatcher in an active standby cluster using Zookeeper. If the primary dispatcher node suddenly explodes or loses power, Zookeeper instantly detects the dropped heartbeat. It promotes a standby node to become the active leader. This new leader then rapidly reads that latest event log from Kafka, rehydrates its memory to know exactly where every car is, and resumes service without dropping a single passenger's destination.
Now for Phase 5, hardware failures and edge cases. Look, a true senior candidate knows that pristine software will inevitably collide with broken real-world hardware.
Consider a scenario where a physical elevator car suddenly loses its network connection. In our system, if a car misses its heartbeat signal by even half a second, just 500 milliseconds, the dispatcher ruthlessly marks it offline in Redis. It immediately extracts all the pending hallway calls assigned to that broken car and dynamically reassigns them to the surviving active cars. The system practically heals itself instantly. And remember to always mention physical safety interlocks. This proves your design is grounded in reality. If a sump pump in the elevator pit detects a hydraulic fluid leak, or if physical position sensors start outputting conflicting data, the local controller triggers an interlock. The software is physically locked out from running the car, parking it safely until human technicians can clear the alarm. Safety always overrides routing efficiency, period. Finally, we reach Phase 6, KPIs and shadow tuning. You've built the system, but we have to prove to the interviewer that we can actually maintain and optimize this beast in live production. We use aggressive monitoring to balance two competing forces, passenger experience versus hardware health. We track passenger wait times fiercely, really focusing on the 99th percentile to ensure no one is waiting forever for a ride. But we actively contrast this against operational hardware metrics, things like car utilization rates and directional reversals per hour. This ensures our fancy algorithm isn't just thrashing the cars back and forth and burning out the motors unnecessarily. Which leads us to our ultimate optimization trick, shadow evaluation. By running brand new dispatch logic invisibly on a shadow engine, fed by live production telemetry from Kafka, you can test a totally new machine learning routing model in real time. You literally just compare the shadow metrics against actual performance to perfectly tune passenger routing, all without ever risking a bad ride for a real user. So understanding how cleanly this distributes state and handles physical constraints leaves me with one final thought for you. What other massive, physical, real-world systems could you completely optimize using this exact same distributed architecture? Keep that in mind for your next interview.